Hello and welcome to the Matter, Energy, and Nutrition video. This is meant to go with the Matter, Energy, and Nutrition activity in the module. So let's start out by talking about matter. So matter is divided into two main subclasses. So we have pure substances. I like to think about these as being made of only one type of particle. More on that later. We also have mixtures. And so let's go into the details here, but pure substances are further broken down into elements and compounds. And then mixtures, we have two different classes of those as well. We have homogeneous and heterogeneous. So what are the differences between all these and how do we identify them? Well, let's get into that. So elements are going to be composed of a single type of atom, and we can find a list of all of them on the periodic table. So copper, for instance, is the stuff that pennies are made out of, and that's an element. So copper is composed entirely of copper atoms. Lead is composed entirely of lead atoms, and so on and so forth. And these are all listed on the periodic table. But what happens if we combine these elements together and we chemically bond them to each other? Well, we end up with compounds. So compounds are when we chemically bond two different elements together, two or more elements together in a definite ratio. And so water is a great example of this. Water is H2O. Two hydrogens and one oxygen bond together to make water. Table sugar is another example. The formula is listed there. And table salt is another example. NaCl. So they're chemically bonded together, the sodiums and the chlorines, and they are in a fixed ratio, in this case 1:1. So one of the interesting things about when we form a compound is the compound has completely different properties than the elements it came from. So what happens here, and we'll get into this more in upcoming chapters, the electrons are going to be rearranged, which is going to mean the properties are going to be totally changed. So table salt, good old table salt, is sodium and chlorine combined together in a 1:1 ratio, and they're chemically bonded to each other. And we're all familiar with table salt. It's delicious and it's relatively non-toxic and it's pretty chemically inert. It's not very reactive at all. But the elements it comes from are sodium. And sodium metal is this shiny silver metal. It's very soft. It actually has a consistency pretty similar to like a cheddar cheese. You can cut it with a dull knife, it's so soft. But it's also violently explosive when it touches water, and it can burst into flame upon contact with air. Chlorine, on the other hand, is a gas. It's green in color, and it's incredibly poisonous. Many people have died accidentally or on purpose upon exposure to chlorine gas. It's been used as a warfare gas. But if you've ever heard about someone killing themselves by accident cleaning their bathrooms, mixing chemicals together, well, chlorine's the stuff that does that. So we have these two very dangerous materials. This one would blow your face off if you put it in your mouth, the sodium, and the chlorine is very toxic, but when we react them together, we get something new with entirely different properties. We get delicious table salt. So just a heads up there, the elements have completely different properties than the compounds that they form. So moving on to mixtures. Mixtures are going to be when we physically stir things together, but they aren't chemically bonded to each other. And with the first type, we're going to talk about what's known as homogeneous mixtures. And homogeneous mixtures is where the composition is uniform throughout. So another way to think about this, I like to think about this as the components of the mixture are dissolved into each other. So homogeneous mixture, stuff dissolves into each other. So like if we were to mix salt and water or sugar and water, those would be examples of homogeneous mixtures. And our other type of mixture is what's known as heterogeneous mixtures, and this is where the composition is not uniform throughout. And so, in other words, our materials don't dissolve in each other. So they give the example down here of pennies in water, and really anything where stuff doesn't dissolve. So like pebbles in water and sand in water, or like a tossed salad. There's lots of food examples. Like a pizza or a tossed salad would be great examples because they're not uniform throughout. We have these components which don't dissolve into each other but are sort of adjacent to each other. So heterogeneous mixtures, they don't dissolve in each other. Homogeneous mixtures, they do dissolve in each other. And mixtures are different than compounds because the composition's variable in a mixture and the materials are not chemically bonded to each other. So let's try and figure out what types of mixtures or elements or compounds, what types of substances we have here. So starting out with aluminum foil, let's begin with B here. This one's easy. This one's an element. So how do we know it's an element? Well, if we go and we look at the periodic table, aluminum is listed there, so aluminum is an element. And carbon dioxide, on the other hand, this is a compound. Formula for carbon dioxide is CO2. We have one carbon combining with two oxygens. They're chemically bonded in a fixed ratio. We have pasta and tomato sauce up top here. So this is a mixture. We have a bunch of different compounds mixed together, and they aren't dissolved in each other. So what that means is this is going to be a heterogeneous mixture. And down here, our air. In air, we actually have a mixture of nitrogen and oxygen and a bunch of other gases, and they do actually dissolve in each other. And so this would be a homogeneous mixture. There we go. So A is heterogeneous mixture, B is an element, C is a compound, and D is a homogeneous mixture. Let's see how we did. Fantastic. We got them all right. So what I'd like you to do now is to pause the video and please complete question number 1 on the activity. Once you've completed question number 1, go ahead and return to the video. Welcome back. Let's talk about energy now. So energy comes in two different flavors. We have what's known as potential energy, and potential energy is energy stored. And so this can come in a few different flavors. It's easy to think about things like if we raise a weight above the ground, or if we have water behind a dam, compressed springs, stretched rubber bands, that type of thing. Those are pretty easy to visualize, but in chemistry it's a little more complicated. The energy is actually stored in the chemical bonds. And so any chemical that has potential energy, we essentially have it stored in the bonds. And what can happen during our reaction is we can actually make new and stronger bonds, and that's what's going to release that potential energy. And so things that have potential energy in chemistry are going to be things like fuels, fossil fuels, food, things like that. Those are all examples of chemicals that have energy stored in them. And so our other flavor of energy is what's known as kinetic energy. And this is the energy of motion. And so this is going to be, once we release that potential energy through a chemical reaction or something, we're going to get this energy of motion. And so one of the main types of kinetic energy that we're going to see in chemistry is going to be heat, though there's other varieties. So things like a car driving down a freeway or water falling over a dam. Those are examples of kinetic energy, but chemistry, usually we're looking at heat as the main form of kinetic energy. You might be wondering, well, how does that work? Well, that is because heat is actually the motions of the molecules. So the random motions of molecules and atoms vibrating and tumbling around, that's heat. So it's just a very, very sort of microscopic version of kinetic energy. So energy is typically measured in one of two different types of units, either in what's known as joules, and that's abbreviated with uppercase J, or in calories, which is a lowercase CAL. And so a joule is sort of a more physicsy unit, and a calorie is essentially how much heat is required to raise 1 gram of water by 1 degree C. More on that later, and the relationship between them is shown here, so we can interconvert between them. So 4.184 joules equals 1 calorie. And so here's the two different conversion factors we can make of this. Oh yes, conversion factors are back, and so are sig figs. And one thing that you may see is you'll see variations of these, like kilojoules. If we stick that K prefix in front, it's going to be twice as big. So 1 kilojoule is going to equal 1,000 joules. And this is one to be very careful of right here. Calorie with an uppercase C is actually a different unit than calorie with a lowercase c. So this uppercase C calorie is typically used if we're talking about foods. So people sometimes call these food calories. And one of these big calories, or food calories, is going to be equal to a kilocalorie, or equal to 1,000 of these regular little calories. So just be aware that calories with a big C is different than calories with a little c. So here we have a question, how many calories, and notice as uppercase C calories, are obtained from a pat of butter which provides 150 joules of energy when metabolized? Well, we have to convert from joules into calories, so we're going to use our ratio right here. We're going to start with that 150 joules. We're going to take this out of our problem right here. Bam, and that's going to become our starting point for this problem. We're going to have to convert from joules into calories. We're going to use the one that puts the joules on the bottom. So we want this one right here. And that allows us to cancel out these joules with these joules. And so that means that we have 36 calories of heat being released by this by the metabolism of butter. And so notice we have 2 sig figs. And this one says 4 sig figs, but I believe on the previous slide this said exact. Unfortunately, that some errors in some of these slides, and I can't fix a lot of them because of the way that they're formatted. So blame the publisher for that one. That one should actually be exact, but our answer should still be to 2 sig figs because we're limited by the 2 out here. And so from there, we can convert our 36 calories into food calories. That's what the question asks for, by using the relationship that 1,000 of these little calories equals 1 food calorie. So little calories cancel, and we end up with 0.036 food calories as our final answer. So please pause the video and complete questions 2 and 3 on the activity.